Starting calculus can be daunting, but one of the keys to starting off on the right foot is having a strong understanding of the fundamentals. In today's video, we will cover some of the most important things to know about functions and discuss some of the important characteristics of polynomials. First, let's look at what makes a function a function. If we look at the function notation, a function is an equation which takes an input value and yields a result. For example, in the equation y equals 3x plus 5, 3x plus 5 is the function, in which you supply the input value x, and y is the result. It is important to be able to determine if a set of data is a function. This can be done by following the guideline that in a function, an input value cannot produce more than one distinct output value. For example, in the table on the left, we can see that the input value 1 gives us two different output values, 5 and 4, which means it cannot be a function. It is important to note that the different input values can return the same output value and still be a function. In the table on the right, we can see that the input values 1 and -1 both return an output value of 5. This dataset is still a valid function. You can also determine if data is a function graphically, using the vertical line test, which states that if a graph contains a function, you should be able to draw a vertical line anywhere on the graph, and it should only intersect one point on the function. For example, if we look at the graphical representation of the data we determined was not a function earlier, we can see if we draw a vertical line at 1, we intersect the data at 2 points. While if we look at the graph of the data that was a function, no matter where we draw vertical lines, it only intersects the data once. Now that we've recapped what a function is and how we can determine if a set of data is a function, we can discuss polynomial functions. A polynomial is a function that consists of the sum of a finite number of non-zero terms, each of which is a product of a number and a variable raised to a non-negative integer power. This is a lot of words, so let's break it down by looking at the function representation. If we look at the leading term, we can see a term consists of a number or coefficient and a variable or input value which is raised to a power n, which cannot be less than 0. N represents the highest power or the degree of a polynomial, and all subsequent terms will have variables raised to lower powers. Polynomials can also be expressed in a factored form, where we can separate the function into simpler building blocks, like the equation 3x cubed minus 2x squared minus 12x plus 8, which can be factored down to 3x minus 2 multiplied by x minus 2 multiplied by x plus 2. With these two forms of the polynomial, we can distinguish important traits about the function. For example, we can use the factored form to determine where the function equals 0, or the x-intercepts. You can do this by setting each factor equal to 0 and solving for x. In our example, we can determine that the polynomial touches the x-axis at 2/3, 2, and -2. Along with determining the x-intercepts, the factors can give insight into the behavior of the graph at the intercepts. This is done using a factor's multiplicity, or the number of times a given factor appears in the factored terms. Simply, this means the power a factor is raised to. In our example, all our factors are raised to the power of 1, and we can observe that they all cross the x-axis. This is because an odd multiplicity indicates the polynomial crosses the axis at the intercept. If one of the factors was raised to an even power, like 2, instead of crossing the axis, the intercept would touch the axis tangentially. The magnitude of the multiplicity also matters, with higher values causing flatter approaches to the x-axis. For example, if one of our factors was raised to 3, the intercept would still cross the axis, but with a flatter approach, similar to a cubic function. We can also gather a good amount of information from the original form of the polynomial. For example, we can gain an understanding of the number of x-intercepts because there can't be more x-intercepts in number than the highest power. We can also quickly determine the y-intercept as the a0 value from the equation. Turning points, or parts of the graph where the slope goes from positive to negative, or vice versa, can be gauged by the rule that there cannot be more in number than the highest power minus 1. Something that is particularly useful is the ability to determine the polynomial's end behavior, or the behavior of the graph as x approaches infinity and x approaches negative infinity. Polynomial end behavior can be discerned from its leading term, where the highest power determines if the end behaviors both reach for the same infinite y or different ones. The sign of the coefficient also has an impact on the orientation of the end behavior. If the highest power is even, then both ends of the polynomial reach towards the same infinite y. If the coefficient is positive, they both reach for an infinitely positive y. And if the coefficient is negative, they both reach for an infinitely negative y. If the highest power is odd, then both ends reach for opposite infinite y's, with the sign of the coefficient determining which side of the graph reaches towards negative infinity and which side reaches towards positive infinity. Screenshot the screen for a quick reference guide on how the leading term affects polynomial end behavior. Now that we've discussed how to pull out the important factors of a polynomial, think about how you might use them to determine a function while looking at a graph, or look at a function and see if you can picture the polynomial in your head. If you liked today's video or have any questions, let us know in the comments. If you want to help us make more of this content, subscribe.